so funny.
Okay, and that's
Different
it.
shapes or different types of
Yeah, so we actually finished the financial math sections of the class last time. So pretty much anything else you want a quiz or a test, you're going to use one of those forms that I mentioned. Or maybe a couple of them, and you're definitely going to reuse them again in your project. So I guess we're going to move on. We're going to move on to something slightly different. Slightly. So the next section is matrices. Matrix algebra. So we're going to study these new objects called matrices, and we're going to be doing a bunch of stuff with them. Include some things that you already know how to do without matrices, but I would like you to learn the matrices way of doing it. Do I have to use matrices? Can I do what I used to do in high school? No, it's very important that you learn how to deal with matrices. They are super important, especially today with AI and everything's being done on computers. A lot of the times, artificial intelligence and a lot of their financial systems and models rely on matrices. They're going to be huge matrices. Thousands and thousands of rows or even millions of rows and columns. But we are going to be dealing with very small ones like 2 rows or 3 rows and 2 columns and 3 columns. Maybe a 4x4 or 5x5 here and there, but for most of our time it's going to be spent with the 2x2s and 3x3s. And I want to talk to you about these guys, just tell you what the basics. We're going to start from the very beginning. Because, yeah, people might not know. How many people have seen these before? So a lot of people have seen it. It was the same thing in my other class, but then when I started asking them questions about it, they all said the wrong answer. So having seen it is not good enough. You need to remember the basic rules. And I think in my other class, like only one person never saw matrices and everyone was like, yeah, we know what this is. And I'm like, oh yeah, how do you multiply these 2 things? Every person who said something said the wrong thing. So I'm going to still start from the very beginning, okay? We're going to build it up. So you might feel bored if you already know this stuff, but you probably don't know it as well as you do, so we're going to be careful. Matrix is a rectangular array of numbers. Now that definition is not good enough for a math person, but for a business person, pretty much anyone else, that's pretty good enough. So example 1, 2, 3, 4. 1 minus 1, 0, 2, 7, 8. Or just 1. So you can use that, or sometimes you can also use square brackets. These are equivalent. So you can write this, or you can write that. However, one thing you do want to make sure that you never actually write is straight line bars. This, with straight lines on each side, is not a matrix. So you include them in parentheses or brackets, not straight line bars. These, when you put straight line bars, it actually means something else. It means determinant. The determinant of the matrix. 1, 2, 3, 4. So, but in terms of notation, you arrange numbers in kind of a rectangular shape. You can see that there's sort of a rectangle here, a rectangle here. This is called a matrix. And it's a very convenient way to encode numerical information. So computers think in matrices a lot of the time. Matrices, by the way, I just said it, is the plural of matrix. So matrix is singular, matrices is the plural. So that's what they are. numbers in the matrix are called its elements, entries, or components. Can use any of those, as well as a horizontal sequence of numbers. This is called a row, and these are numbered from top to bottom, starting at 1. Vertical sequence is a column. And these are numbered left to right. And again, starts at 1. So, for example, matrix 1, minus 1, 0, 2, 2, 1. Then, if I look at the horizontal list of numbers here, this is called row 1. That is row 2. Start numbering them from top to bottom, going down. If I look at the same matrix, 1, minus 1, 0, 2, 2, 1. When I look at the vertical sequence of numbers, these are called the columns of the matrix, and they're numbered from left to right. That's column 1, that's column 2, that's column 3. We can talk about the size of a matrix or the dimensions of a matrix, and that's just basically describing the number of rows and columns. Matrix with n rows and n columns is a m by n matrix. Okay. So this part here is read m by n. Okay. So this, for example, is what? This is a 2 by 3 matrix. You being able to identify the size of the matrix is going to be very important. There are certain calculations that are going to depend on the size of the matrix. So this is the size or dimensions on here. If m equals n, the matrix is called square. It's called a square matrix. We can call it n by n, or so a 2 by 2, or a 3 by 3, or a 7 by 7. These are called square matrices. Now there are some operations that can only work with square matrices, like inversion and determinant. You can only actually find with a square matrix. There are a bunch of things that only work with square matrices. And I've had a friend who's been hired for very hefty prices by firms to kind of help them figure out how to get something done, some kind of business idea that they want to actually apply to their system, and basically goes in there day 1 and say, oh, this thing you're trying to do is pretty much impossible. And they say, why? Well, if you code the information this way, it's not a square matrix, so what you're trying to want to do is impossible. Thank you. basically thousands of dollars, because someone in that business firm did not pay attention to the fact that, oh, this thing we're doing can't be done because it's not square. So there are some things that we can only do if they're square. We will get there, well, not today, but soon. What else do I want to do? Oh, maybe some notation. How about notation? We can name matrices. Usually with uppercase letters. So I can say A equals the matrix 1, 2, 3, 4. And from then on, whenever I write uppercase A in a formula, you will know I'm referring to that guy. Scalars, or what you will know as a constant, may be represented by lowercase letters. So if I mention something to you, like if I write down a phrase on the board like Ka, you're expected to know that I'm referring to a constant in this case, and I'm referring to a matrix in that case. Right? Like if I write them together. We can also name entries based on their position. Usually we do with a corresponding lowercase letter with the matrix that I originally named, but it's going to have subscripts. So, for example, it would look like lowercase a and an ij. So if your I and j are each one digit long, there's no ambiguity here. If there are several digits long, you might put actually a comma between the I and the j. And aij is the element in A, the uppercase A, in the ith row and jth column. So, for example here, so that this matrix is 2, 7, 8. I can talk, if I call this guy A, I can refer to A11 and A12 and A13 and A21 and A22 and A23, right? These will all refer to certain numbers in the matrix, and this is referring to the element that is in the first row and first column. Rows are numbered by, from starting at 1 going down, and columns starting at 1 going left. So this is the number in the first row, first column. This is the number in the first row, second column, which is going to be that. First row, third column, which is going to be that. Second row, first column, bless you, is going to be that. Second row, second column is going to be that. Second row, third column is going to be that. So those would refer to the numbers in the matrix. And for emphasis, at any given time, I refer to as, I might write A with a subscript n by n if I specifically want to identify the size. And there are going to be times when I specifically want to identify the size. Or I might refer to A as, in parentheses, write Aij, and then put like m by n down here. So that also refers to an m by n matrix where the elements are being called a subscript ij. And oftentimes if we want to give a formula with matrices, that's how we're going to do it. A lot of times when we're proving something with matrices, that's how we're going to we're going to use this notation. I'm not going to prove anything for you guys, but I'm just going to kind of give you the information. But at any given time, I might want to use that for definitions. Okay. Those are all the names. We'll try a few more definitions, but told you about that, told you about that, told you about that. So that's square matrices. Okay, let's do some operations. So now we're going to learn to do algebra with matrices, matrix algebra, operations on matrices. So that's what matrices are, that's how we might refer to them. Now let's actually talk about some operations we can do with them. We can do math with these matrices, that's why we invented them. Probably the first thing I want to talk about is equality. Two matrices A and B are called equal, and we write A equals B if they are the same size and corresponding entries are. Now, it is not lost on me that this seems like a painfully obvious definition, but this is going to be a theme. There are going to be times when I'm going to write certain things down, and to you they will seem obvious. It is actually important that I write these things down because it turns out that in very special circumstances, matrices become quite non-obvious. So I want you to be able to tell the difference between the obvious situations and the not obvious situations. So every now and then I'm going to write down a definition like this, or like, well, what else would it mean to say they're equal? But it's actually important because there are times when the matrices will behave in a certain way that's like, well, that's weird. And so I'm going to be pointing it out. So I have 1, 2, 3, 4, and I tell you that it's equal to x to y plus 1 and 4. You would be able to say from this, me telling you this would imply that you actually automatically know that x equals 1, and you automatically know that y plus 1 equals 3, so that your y must be 2. So you'd be able to solve the equation by matching up corresponding components. There's something called scalar multiplication. A matrix can be multiplied by a number. So K is a scalar, which just means a number, constant. A is a matrix. Then we define Ka to be equal to this matrix. Say this is n by n, n by n. In other words, you want to multiply a matrix by a number, it's the same thing as multiplying each individual component by that number. And this is called scalar multiplication. So this is referred to as scalar multiple. And what you do is you multiply each component or entry by K. So that again might seem obvious. But we'll get to a non-obvious operation pretty soon. Talk about matrix addition. We can add two matrices. So let A m by n and B m by n be matrices. Note they have the same size. Right? This will only work if they have the same size. Right? They're both n by n's. So we define the addition of these two matrices, A plus B, by, well, again, you add corresponding entries. Right? So you just add the guys who line up. So if I'm adding these two, I would add this with this, add that with that, add that with that, add that with that, and write a new matrix. And the result will also be n by n. Right? So n by n, again, is the size. So I'm saying, here's a matrix with m rows and n columns. Here's a matrix with m rows and n columns. If I add them together, I get another matrix with m rows and n columns, and the entries in that matrix is just going to be me adding corresponding entries from the individual matrices. Yeah, I'll do some examples. So it also works, as you might guess, with subtraction in pretty much the same way. At this point, I think we have some examples. You might be bored writing down all these definitions. So let's just make sure you understand the operations that I just mentioned. Scalar multiplication and addition. These are very important. So here's an example. Here, A equals 1, 2, 3, 4. B equals 2, 0, 1, minus 3, 1, 4. C equals 7, 1, minus 1, 0, 1, 2. D equals 0, minus 1, 2, 2. Compute. A plus B. A plus B. D minus A. E minus C. 2A. 2D minus 3A. 1/2 D. And if x plus d equals a, I want you to find x. Get through these examples. Yes? So most of what I've given you so far are just straight up definitions, not really something to understand, just something for you to know. This is what a matrix is, this is what I call it, blah, 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 blah. Right, just making sure we have the same language here. Understanding how to do math with them, that's something you need to understand how the mechanics of this actually works. So, I'm looking at A plus B. That's just me saying, okay, I'm taking the matrix 1, 2, 3, 4, and I'm going to add to it the matrix 0, minus 1, 2, 2. And what is this going to look like? Let me try to think of what is going to be the result here?
1, 1, 5, 6.
1, 1, 5, 6. How did we actually get that? Now, in general, you don't have to write this down. You're at a point where you're adding matrices. I'm going to assume you know what you're doing. But just to make sure we know what we're doing, we add both entries in the 1, 1 position, add both entries in the 2, 2 position, add both entries in the 2, 1, in the 1, 2 position, in the 2, 1 position, and add both entries in the 2, 2 position. You'll add corresponding components. This adds up to 1, that adds up to 1, this adds up to 5, that adds up to 6. So far, so good. One of the things with matrices is that at any given time, the math that you're doing is not going to be complicated. You're just like adding or multiplying numbers. So it's basic arithmetic, but the mistakes happen because you're doing a lot of this all at the same time. And you just mess up sometimes. So you want to be careful of that. So things might look easy sometimes, but don't underestimate them, because them being easy kind of makes it hard. It's easy for you to like zone out and not pay attention to something. A plus B. What is this? Yeah.
3, 2, 1, 0, 5, 4 on the bottom.
3, 2, 1,
0, 5,
0, 5, 4. No.
4. Oh, B.
Can't you not add them?
You cannot add them. This is undefined. Okay? So remember that thing where I said they had to be the same size? That was an important statement. You can't add them if they're not the same size. So that's undefined. Because what's the size here?
2 by
2 by 2. What's this?
2 by 3.
2 by 3. So we're 3. 2 by 3. And that's also 2 by 2. So you can only add or subtract the 2 by 2s and the 2 by 3s. They cannot be added to each other. So size is very important, that they're actually exactly the same size. There are other operations where the size matters, but they don't have to be the same size. For addition and subtraction, they have to be the same size. C. B minus A. So now once I'm doing an addition or a subtraction, the size is going to be important. I notice these are both 2 by 2s, so that actually makes sense. I'm going to have 0 minus 1, 2, 2, minus 1, 2, 3, 4. And again, you subtract corresponding entries. So 0 minus 1, minus 1, minus 2, 2 minus 3, 2 minus 4. So that's going to be that. That was C. B minus C, is that possible? So yes, B and C, they have the same size. So this would be 2, 0, 1, minus 3, 1, 4, minus 7, 1, minus 1, 0, 1, 2. 2 minus 7, 0 minus 1, 1 minus minus 1. See what I mean? You see how that happens? Like I thought 1 minus 1 and then I wrote a 0. It's actually 2 because it's minus a negative 1. That's where the mistakes happen. You just like you just slip up every now and then. So be careful. 3 minus 0, 1 minus 1, 4 minus 2. So that would be the answer here. So this is a scalar derivative. In other words, this is 2 times 1, 2, 3, 4. And how do we do that? Well, the rule says you'll multiply each component by the scalar. So while you might not have to write this, what's actually happening is you're going to take the 2 times the 1, the 2 times the 2, 2 times the 3, 2 times the 4, and at the end of the day you'll get 2, 4, 6, 8. So that's going to be that. Now we have 2d minus 3a. So we're subtracting 2 scalar multiples. So the first thing we have to figure out, would the sizes match up? Well, a is a 2 by 2 and d is a 2 by 2. Multiplying by scalars does not change the size, it just simply multiplies each corresponding entries. So these two will also be 2 by 2, which means it's possible to actually add them. So I'm going to go ahead and actually add them. PEMDAS still applies. I'm going to apply the 2's first, the scalar multiples first. So this is a 0, minus 2, 4, 4, minus 3, 6, 9, 12. And then I'm going to subtract those. 0 minus 3, minus 2 minus 6, 4 minus 9, 4 minus 12. So that's the answer there. E. We have 1/2 E. Well, that's just a scalar multiple. It's just 1/2 times 0 minus 1, 2, 2. Just threw this one in there so you know, don't have to just have whole numbers, you can have fractions, you can have decimals, you can have radicals, you can have pies, you can have e's, you can have whatever. Usually in the context of business, you're just going to have numbers. It's possible that within a matrix you have other matrices, and these guys are called tensors, and that's a whole different story. I don't think it's not very likely that you need to understand those guys. They're a different animal altogether. Look at H. So here I know that x plus d equals a. Now I know that a is a 2 by 2. I know that d is a 2 by 2. So this means x is also 2 by 2, because otherwise me writing down this statement wouldn't make any sense. So I know it's a 2 by 2. Now, what we can do here to solve for x is to, well, subtract d from both sides. Now, what actually happens, why I'm allowed to do that, is because I can think of this as, well, I don't have to write that now. Let's write x plus 0 minus 1, 2, 2 equals 1, 2, 3, 4. What I can do then is subtract d from both sides, so I can minus 0 minus 1, 2, 2 equals 1, 2, 3, 4 minus 0 minus 1, 2, 2. This is going to be x plus, I'm going to have a bunch of zeros here, equals 1, 2, 3, 4 minus 0 minus 1, 2, 2. And of course, by the definition of addition, this is just adding a bunch of zeros to the card components of x. So that just leaves us with x, and that's your a minus d. So this actually makes sense. Now again, seems obvious. There's a point to me writing that down because there are times when things are not going to be so obvious. So when it comes to addition, essentially your intuition from regular addition with numbers is going to work out for you. So that's not, you can feel comfortable like adding or subtracting something from both sides. Multiplying and dividing something from both sides is a whole different story though, not obvious at all. So in other words, here, this will be 1, 2, 3, 4 minus 0 minus 1, 2, 2. So the x must actually be 1 minus 0, 2 minus a minus 1, gives you positive 3, 3 minus 2, and 4 minus 2. So that's what the x value would have to be. If I take that matrix and add it to that matrix, the result is going to be this matrix. Any questions before we move on? So addition and subtraction, pretty straightforward. Just make sure you're adding things that have the same size. Scalar multiplication, also straightforward. Putting a number in front of a matrix just means multiply everybody in that matrix by that number. Let's talk about matrix multiplication. Now, for those of you who already know about matrices, you would know that here's where the obviousness kind of ends. For those who probably never seen matrices before, you're probably going to think a certain thing. Like 1, 2, 3, 4. 0 minus 1, 2, 2. Let's say I wanted to multiply a times e. What would you guess you would do? Like if anyone who's never seen matrices before. Right, just tell me what you think we're going to do. It's okay to be wrong. Yeah, so don't worry about it. Yeah, just go with a guess.
So the first number in A is 1, first number is D, and D is 2, so 1 times 0.
Okay.
2 times -1, 3 times 2, 4 times 2.
Yeah, multiply the corresponding entries.
Yeah.
Yeah, that's not how we do it. Now, to be perfectly clear, it makes total sense. You would think, well, how else? Why would you do it any other way? Yeah, not true. Right? That's not how it works. Now, someone who knows about matrices, tell me what the actual answer is. How does it actually work? What is the actual answer here if I wanted to multiply these two?
Don't you use a determinant?
No, you don't need determinants at all. No. Yeah.
Like,
Who's
the
the
B.
X?
1 times 0, 3 times -1, and then 2 times 2, 4 times 2. No.
Is 3 times -1? No.
Yeah.
Yeah. Go.
If you multiply diagonally the same matrix.
What do you mean multiply diagonally?
1 times 4, 2 times 3, 0 times 2, -1 times 2.
No. That's determinant. You're thinking determinant. That's something else. Yeah.
Is it 1 times
Yes.
0, 2 times 2, 3 times -1, 4 times 2? Oh, yeah.
Oh, I know.
Is it 1 times 0, 1 times 2?
Okay.
Oh,
Let's-
I have an idea.
Row times
You
first
multiply
column.
something
All right, let's get it.
Is it row by column?
Yeah.
Row by column.
Is it row by column?
Okay.
You multiply
You actually multiply rows by columns.
Yeah.
So it's going to be 1 times 0 plus 2 times 2.
What? That's confusion.
Then over here, you're going to have this times that. You're going to have 1 times -1 plus 2 times 2 again.
Oh no.
Then in the next row, you're going to have this row times that. That's going to be 3 times 0 plus 4 times 2. And then you're going to have 3 times -1 plus 4 times 2. And that's going to give you 4, 3, 8, and that's 8 minus 3, 5. That would actually be the answer. Okay? Now, not obvious at all. Why in the world would you multiply things in that convoluted way? Right? So, I'm going to tell you how to multiply the matrices. As for why is this the way we have to multiply matrices, that's probably a discussion for another time. You probably don't need to know it, but I might get excited and tell you anyway. But yeah, that's how you would multiply matrices. Let's actually figure out how we want to do it. To first figure that out, we have to talk about something called a dot product. Okay, so let's say we have a row matrix. That's what we call a matrix with just one row. Let's say it has A1, A2, A3. And let's say we have a column matrix. That's what we call a matrix with one column. That's B1, B2, B3. Note they have the same number of things. We define what's called a dot product between these guys in the following way. I can say A1, A2, A3, dot product with B1, B2, B3. Okay, so this is called a dot product. There's an equivalent thing in Calc 3. I'm not sure if anyone would ever have to take Calc 3, but it's essentially computed the same way. And the result of doing that is to multiply the corresponding entries and add them all together. So it's A1 times B1 plus A2 times B2 plus A3 times B3. So that's how you dot it. And it's very important that the row is on the left. Row on left. And the column is on the right. Again, the why you don't have to know, although I might tell you anyway, but that's important. The order in which you're doing this actually matters. And so now, here I can define matrix multiplication. If A is an m by n and B is an m n by p, the sizes are important. I'd like you to pay attention to these numbers. Notice that, for example, the inner numbers are the same. If you randomly do that, that's actually an important thing to consider. Okay. So our matrices we define A times B to be equal to the matrix C, and C is actually going to be an M by P matrix, where the Cij, so when you multiply two matrices, you're going to get another matrix. That's going to be the size of that matrix. How you compute each entry is going to be the following. It's going to be, what you put in the ij position is going to be the ith row of A dot product with the jth column of B. You do that every time to compute each component of C. And that's matrix multiplication. So let's actually see how that's going to work out. Example. Let's say I want to do 1, 1, minus 1, 2, and I want to multiply that by 1, 0, 1, 1, 1, minus 1. We'll make this a 2. Now, first thing I want you to appreciate, these two are different sizes. And for multiplication, we don't actually care that much that they're a different size. What we do care about is that the sizes match up in a certain way. One thing you have to realize is that this here is a 2 by 2. This is a 2 by 3. The inside numbers must actually be the same. The outer numbers actually tells you some important information too. The outer numbers tells you what the size of the resulting matrix is going to be. This gives size of result. So essentially, matrices, when you're multiplying them, can be of different sizes. However, they have to be arranged in a certain way. Once you put them side by side, the inner numbers have to match up. And the answer is going to be the outer number size. So I know that if I multiply these two guys, the result is going to be another 2 by 3 matrix. So I know the answer is going to be, it's going to have something that looks like this. There are going to be 6 entries arranged in that fashion. Now, how do I figure out what the entries are? Well, notice that this is the 1, 1 entry, this is the 1, 2 entry, this is the 1, 3 entry, this is the 2, 1 entry, this is the 2, 2 entry, this is the 2, 3 entry. Okay? So this is like your C2, 1. I'm going to be replacing these two. C1, 2, that's your C1, 3, that's your C2, 2, that's your C2, 3. Right? So that's these guys I just identified. How do you find each of them? You're going to do this operation, which I defined earlier. So, what we're going to do with this guy is, what goes in the 1, 1 position? Well, the first row of the guy on the left, dot product with the first column of the guy on the right. So I'm going to do that thing where I go from here to here and multiply corresponding entries and add them together. So this is going to be 1 times 1 plus 1 times 2. Now you add those together, you're going to get 3. 3 goes in this position. And you pretty much do this for the entire thing. So in position 1, 2, you need the first row of A, the guy on the left, dot product with the second column of B. First row, second column, same idea. 1 times 0 plus 1 times 1. So what goes in here is the number 1. We're going to do it again in the 1, 3. First row times third column. 1 times 1 plus 1 times minus 1. That gives you 0. That goes in this position. Now, you know there's no more matrix left, so that kind of closes it, but there's a second row. For the 2, 1, second row times first column. So I'm going to have a minus 1 times 1 plus 2 times 2. Then second row, second column, this times that. We're going to have minus 1 times 0 plus 2 times 1. Second row, third column, minus 1 times 1 plus 2 times minus 1. Simplify those numbers and you would get that 3 is here, 2 is here, and minus 3 is here. So that's actually the result. And we have 2 minutes left, so I'm going to give you some examples to try for next time. So try these for Friday, I want to say. We see each other again on Friday. So here are the matrices. A is 1 minus 1, 2, 1. B is 2, 0, minus 1, 1. C is 1, 2, 3, 0, 2, 4. D is 1, 0, 0, 2, 3, 1. And I want you to find AB, BA, AB, DA, AC, CA. There's a reason why I'm asking you to find them in both orders. And if you try them by Friday, you'll notice what that reason is.
Is that a 6 or a 0 on D?
These are all zeros. There are no 6s anyway.
Okay.
So these are all zeros. Try those for next time. Let me know your results. Stop there.